Hello everyone, today we are going to discuss how we can derive heat equation. So heat, it's a mathematical equation, a partial derivative equation, which govern how heat is flowing from one place to another. So for the simplest case, in this study we will consider a one-dimensional rod, and we will try to figure out how heat is flowing through this rod. So this rod has start at x equals to 0 and it has length to x equals to L. So let me draw here a figure. Not this one, so let's draw a rod. So this is a rod and it has a cross-sectional area A. So this is x equals to 0 and x equals to L. So first of all, the important thing is here we consider that the like we introduce a temporary quantity that is thermal energy per unit volume, and we treat it as unknown variable. So the thermal energy, or it's called thermal energy density. Thermal energy density, that is E equals to xt equals to thermal energy density. Okay, so this is like we are treating it as an unknown variable now. Okay, so in our figure there is we consider a small area, a small like small page. We just start from x and it's x plus delta x, and if we consider if we move backward it will be x. Okay, so the thermal quantities are constant across a section. So the thermal quantities are constant, and the rod is one dimensional. Rod is 1D. Okay, and rod is perfectly insulated. That is very important. It is insulated because no energy is coming into the system and no energy is leaving out from the system, so no thermal energy can pass. So the dependence on x and t correspond to the situation which the rod is uniformly heated. The rod is not uniformly heated. So for example, the rod is hot at some point and it is cold at some point. So this is how energy flow through the rod. So here this is the coordinate x, y and z. Okay, so now let's talk about heat energy. That is an important concept. So heat energy. So after setting up our system, let's talk about heat energy. So we only consider this small patch between x and x plus delta x as shown in this figure, and the thermal energy is constant in this. Like we assume that thermal energy is constant. Thermal energy density is constant in this patch. So the total energy in this volume is a product of energy density and volume. So total energy, total heat energy in this slice or in this small page, heat energy is equals to thermal energy density times area times delta x. So this is our volume of this small page. So now we have an unknown, that is energy density. Now we have heat energy in this form, and so this is, let's name it 1, this is 2. So now we will talk about conservation of energy, that how energy is like conserved in our system. Conservation of heat energy. Conservation of heat energy. So here, so the like rate of change of heat energy in time equals to heat energy flowing across the boundaries, heat energy flowing across boundaries per unit time plus heat energy generated per unit time. So what it mean? It mean the heat energy between x plus delta x changes in time due to only heat flowing across the edges. So heat is only flowing through the edges of x plus delta x, and heat is generated inside. It can be positive or it can be negative. So based on which direction your delta x is. No heat energy changes are due to flow across the lateral surface, since we have assumed that lateral surface is insulated. Okay. The fundamental heat flow process is described by this equation here. So now this is called conservation of heat energy for a small rate of change. So we will give like the conservation of heat energy. This is given by d by dt into E rate of change of heat energy. So heat energy is given in equation 2. So we will simply write Ex of t a delta x. So this is equation 4. Now, so why we use partial derivative here? We use partial derivative here because x is fixed in this case. So now the second is heat flux. So second, the second important part of above equation, the one that I have written in term of words here, like this one, is heat flux. What it mean? It mean, let me put it here so that we can, okay. So here heat flux mean that heat is flowing. Heat flux is given by this phi. So phi into x plus delta x in t. So heat flux is the amount of thermal energy per unit time flowing to the right part of the surface area. All right. So if phi of xt is less than 0, it means heat energy is flowing from left. Okay. Heat is flowing from left. Heat flowing per unit time across the boundary is, so heat flowing, if it is positive, if it is greater than 0, it's flowing from the right. So that's easily understood. So heat energy flowing per unit time across the boundary of the slice is given by, so heat energy flowing per unit time across the boundaries of slice is given by phi of x t a minus phi of x plus delta x t into a. So okay, now we have heat source. So let's talk about heat source. So here, this is the term heat source. It is the heat that is generated inside the system. So heat source is q of xt is heat per unit volume, heat energy per unit volume generated per unit time. Okay, so this is, so now we'll put everything together and we'll put everything together to see the conservation of heat energy within this thin slice. So that is the first part. D by dt E dot delta x a is approximately equal to, we'll see why this is approximation. So because here we are taking so many assumptions and keeping a lot of things constant. Phi q, no, this is q, this is the source qx of t, and it's generated a dot x delta x. So heat generated per unit volume per unit time. So here we will, so a is cancelled. Okay, so a is cancelled, there is a here as well, so this is cancelled, this is cancelled. So now to simplify, we will divide delta x on both sides. So partial e by partial t is is approximately equal to phi of xt minus phi of x plus delta x t divided by delta x plus q of xt, because one delta x is cancelled with this one here. So after looking at this equation, we can take the limiting limits, like we can take the limit delta x approaches to 0 here. So limit just to so it can give us the definition of derivative. Okay, so delta e by delta t is equals to minus of, like, this minus sign, we will get it after some, like, it is just a result of simplification, plus q. So this is the heat equation of heat conservation equation. So this is the conservation equation. We can derive the same equation by using integral method, so integral conservation law. So that is more fundamental, but we'll stick to the method that we have used. So this is another important equation which we use later. So now we will talk about here, we'll talk about temperature and specific heat. The temperature and specific heat. So our goal is to derive the heat equation, not the conservation equation. So for example, the temperature is given by u of xt. So it is a function of time and the space component x. So it is temperature. So not thermal energy, it is not a thermal energy density, it is temperature. So now the specific heat is given by c. It is specific heat. So what is specific heat? It is the heat energy that must be supplied to a unit mass of substance to rise the temperature by 1 unit. So for example, if you have 1 kg of mass and you want to increase the temperature by 1 unit, 1 degree centigrade, then it is like the amount of heat you provide, and that heat is called specific heat. So thermal energy. So the another important thing is thermal energy. So here, first of all, like, we will talk about, so the number density or mass density. So this is mass per unit volume, it's usual density. So the total thermal energy in any thin slice thus is so the thermal density, in the beginning we just pick thermal density to be E. Now we are deriving it in more mathematical way or more physical way. So Cx, it is the specific heat time the temperature xt time density A and delta x. This is the thermal energy density or thermal energy density. So previously we have written thermal energy density as E of xt into A delta x, which is C of x U of xt rho A delta x. So this is the equation we have now. So here, from here we can easily find that Ex of t is equals to C of x into U of x t into rho of x. So this is the temporary variable that we defined at the beginning. So here, this equation, this is E. So now what we will do, we will take the equation, the conservation equation that we have is equals to minus d phi by dx plus q. We will put this E here. So after putting this E here, C is independent of time, rho is independent of time, so they both will stay out of integral, they will unchanged. The only thing is uxt divided by delta t minus equals to minus d phi by dt, and this phi is function of time and temperature, time and x, plus qx of t. So this is the equation. Now here we will use Fourier law, because like this equation is regarded as one equation in two unknowns. The temperature u of xt is unknown and phi of x is unknown. So what we will do, so here if the temperature is constant in the region, no heat is flow. Okay, so if T is constant, no heat is flow, no heat will flow, no heat will flow. So the second point is, if temperature difference, if there are temperature difference, the heat energy flow from hotter to colder region. Okay, that is heat flow from hot to cold region. Number 3 is the greater the temperature difference, the greater the flow of energy. So greater temperature difference, greater heat flow. Number 4, the flow of heat energy will vary for different material even when same temperature difference. So if material is different, then the heat flow will be different even if you keep the temperature same. So Fourier recognized the properties from 1 to 4 and summed up by this formula. So this is all those properties that I just mentioned are given in this formula. Fourier wrote this formula as it is. This is known as Fourier law of heat conduction. So Fourier law of heat conduction. This is Fourier law of heat conduction. So du by dx is the derivative of temperature with respect to temperature. So it's a slope of temperature or gradient of temperature, right? Okay, if partial u by partial x is greater than 0, then heat is traveling from right to left, and if it is less, vice versa. So let's plug the value in the above equation. So C rho du by dt minus d by, oh, this is d by dx, d by dx into k naught du by dx plus q. So C rho du by dt is equals to k naught d2u by dx square plus q. So now we have a second order differential equation. So this is heat equation. So we will if there is no source, q equal to 0, for example, there is no source, and then we divide everything. So this is capital K. So du by dt is equals to k naught divided by 0 d2u by dx square. So this is the heat equation. Here k small k is equals to capital K naught divided by 0. This is called thermal diffusivity. And our heat equation in this case is given by du by dt is equals to small k d2u by dx square. So in some book it's written as ut is equals to q xx. So this is the heat equation, and we derive it in today's lesson. So this is it for now, and I will see you in the next lesson. Thank you.